Hey guys, Mrs. Frazier here. In this video, we are going to talk about sampling and normal distribution. This is going to go in depth and will help you finish the click and learn that you have to do as an assignment. In this video, we are going to talk about samples and how they apply to populations. We're going to talk about how to find the mean and what that means. We are going to learn about standard deviation and how to use it. In the next video, we will talk about standard error of the mean. I want you to pause the video for a minute and think about these things. How is this graph interpreted? What is the x-axis? What is the y-axis? Describe the error bars. What do you think these are telling us? Take a moment to write down your thoughts in your notebook and then press play when you're ready to begin. Let's take a look at the graph. It says figure 1 is looking at the mean length of seedlings after 1 week in the dark or in the light. So we are looking at seedlings. If you can think about seedlings in your head, they're tiny and there are tons of them if we are looking at a population. So this figure, this graph is showing us the mean length of those seedlings in the different populations. A mean, how do you get a mean? That is an average, and you get it by adding up all of the individuals that you're measuring and divide it by how many. Well, to get an accurate mean, wouldn't you need to measure all of the individuals? How do you do that when your population is so big that it might be impossible to do that? Would you want to go measure a bunch of little seedlings in a field? Scientists don't have the time or the money to do that either. But there are ways around this. We are going to learn how to apply statistics to smaller sample size so that we can represent the population accurately. Statistics are thrown at you all day, every day. Think about the news right now. What do you see? Biden is leading in the polls by 23 points. Or the next day, no, now Trump is ahead of American voters. So is there someone there that is asking every single voting American to ask who they're voting for every single day? No, it is typically not possible to measure every individual in a large population. So where are we getting these numbers? A sample of the population is taken, and a sample is a collection of individual measurements randomly drawn from a population. The word random here is very important because it has to accurately represent the whole population. Let's look at this picture. If this is our entire population of Americans, a sample has to be collected from all across the country, including lots of different people, so that our sample size has a little bit of everything and represents the population as a whole, hopefully. And then we apply our findings from this sample. So let's say all of these came out with Biden is the winner. We apply that idea and we say that the whole population is thinking that way. I hope you're thinking that there would be a lot of problems if it was that simplistic. It is not that simple. If we are going to take a sample of the whole population, we need to apply statistics to the sample in order to describe it in terms of the population. There is more to it than what I just described. In statistics, each sample is defined as a collection of a number, which is n, of measurements. So this sample is going to have 1, 2, 3, 4, 5, 6 different measurements because the sample size is 6. So in this case, our n equals 6. Let's summarize again the difference between a population and a sample. In a population, the measurable quality is called a parameter. So in this case, our population, the parameter would be everyone in the United States. And the population is a complete set, meaning everyone in the United States would be a measurement. And because of this, the reports are a true representation of any findings because everybody was tested. In a sample, the measurable quality is called a statistic. The sample is a subset of the population. Reports have a margin of error and a confidence interval, which means that there is going to be some mistakes when we are taking a sample and applying it to a population, but we can calculate how confident we are in our conclusion. A sample is a subset that represents the entire population. But there is and there could be differences between the sample and the population, so scientists must do everything they can to reduce this margin of error. Before we move on, I just want to emphasize again that an individual measurement is part of a sample taken from the larger population. A histogram is a type of graph that you're going to see a lot as we're studying populations. A histogram is a display or an illustration of the frequency of measurements in a sample. This word frequency means how many. And remember from previously, I emphasized that what is a measurement? It is a individual from the sample. So what is this telling us? In this example here, we have time and then the count. So at 40, there is no units, not a good graph. At 40, there were 34. At 60, it's coming up here to about 251. So it's telling you if we're looking at a sample size, out of that sample size, 762 of them were at this time. It is different than a bar graph because bar graphs are looking at specific categories and you kind of see gaps between them. In a histogram, it is a range of number. You are moving ahead. Let's look at this example of a histogram that I found on the County of San Bernardino website. And it is telling us how many cases by age of COVID there are in the county. And I wanted to point out a mistake. They put gaps between their bars. And what this is telling me is that 0 to 14, 348 0 to 14-year-olds have been diagnosed with COVID. And then 254 for 15 through 19. But this gap is kind of telling us that they did not count like 15 and a half-year-olds. They went up to 14 and then they jumped over to 15. And that is why there shouldn't be spaces between your bars in your histograms. Researchers assume that a series of measurements taken from a population will be normally distributed. This means that the majority of the population is going to be around the mean, and then from the mean there's going to be outliers that taper off. For example, if we're talking about height, we know that on average, women are about 5'4". But obviously there are some really tall women and there are some really short women. But most women fall around this mean. The mean value of the population is represented by the peak of the bell curve. So this is called a bell curve because it is kind of shaped like a bell, I guess. And the top of the bell curve right here is always going to be the mean in a normal distribution population. Let's take a look at the graph down at the bottom. This is showing the distribution or spread of a random sample of individuals taken from a normally distributed population. So this means that a population that has a normal distribution like the one we just talked about, a sample is taken from that, and these are our measurements of the sample individuals. And you can see that they are we drew this red line bunching up around this mean, and it tapers off on the edges. Each one of these bars is representing the group of the amount of individuals from that sample that measured in at, so let's say here's 58 kilograms, 16 individuals measured in there out of the sample taken from a normally distributed population. And you can see, and this is what scientists really bank on, is that the sample is going to represent the normal distribution just like the total population. It is time for a check-in. Pause the video, answer these questions in your notebook, and get ready to move on. To help us learn about sampling and normal distribution, we are going to use a computer simulation. You do not need to have access to that simulation during this video, but I will give you access to the link when we do the assignment in class or as homework. The simulation is run by a program that calculates a random sample value from a normally distributed population of infinite size. What does that mean? It is pretending that there is this huge infinite population, and every time you hit resample, it is taking a calculation from that sample that you're specifying. The red line that is produced on the graph that is produced when you press resample is the characteristics of a normally distributed population with the indicated parameters. So here is where you set those parameters. So it is set at a population mean of 50 with the standard deviation of 10, and it created this bell curve. And why did it create a bell curve? Because it told us that this infinite population is normally distributed. The blue line, so this one right here, is the mean of a sample. So in this case, the sample size is set as 4. So you can see 1, 2, 3, 4 measurements taken. That is of that sample size, and this blue line is representing the mean of that. And notice that the bell curve is representing the entire population, not the sample size. So if we look, this mean is not at the tip, the peak of the bell curve. So our sample size is not totally representing the normal distribution of the entire population. The simulation calculates the mean and standard deviation for you, but it is imperative that you understand what those calculations mean for what you're trying to figure out. The mean is the measure of the average of the distribution. But when you look at the parameters or you look at what's given to you in the simulation, you see a population mean and a sample mean. What are the difference between the two? The population mean is the average of the measurements of the entire population. And remember that it told us that the population was infinitely sized in this case for the simulation. So if we counted every single individual, the population mean is the average of that. The sample mean is based off of the sample size that you choose, and it is the average of that sample size. So if your sample size is 4, then it's only taking the average or the mean of those 4 measurements. The standard deviation is a measure of the variation. What that means, it's telling us specifically how spread out are individual measurements in the sample from the sample mean. So here is a sample from a imaginary population. My n is 5 because my sample size is 5 individuals, and these are the measurements that I got in kilograms, whatever these little creatures are, these are what they weigh. So if I find the mean, I add all of these measurements up and I get 15, and then I divide it by n, or the number of measurements, and I get 3, and that is my sample mean. So what standard deviation tells us is when you get this calculation, which we're not going to do the whole calculation, the computer's doing it for us, it's kind of long and you'll see that later, but it tells us how spread out these individual measurements are from the mean. So if my mean is 3, you can kind of see that there's a difference between this measurement and 3, and there's a difference here between 3. So how far, what is the variation between these measurements and the mean? This individual right here, for example, would have a standard deviation of 0 because it is not spread out at all from the mean, it equals the mean. Why do we care about this? I mean, an average is an average. Why do we need the standard deviation? Well, let's say there is another imaginary sample size, and the measurements we got for the individuals are this. So again, our sample size is 5. When we add them up, we get 15. We divide that by n, divide it by 5, we get 3. So our average is the same as this other population, but look at the difference. Does 3 look like a good representation of this? Look at these individuals, 1, 1, like you just have this really big outlier. So the mean is a good starting point, but it is not good enough by itself because it doesn't accurately describe what the data set looks like. This data set, for the most part, the mass is very small for the individuals. Here, it's larger. If we were going to compare these and we were just looking at the averages, we would conclude that these data sets are the same. But looking at them, they're not the same. That's why we have to continue past mean to draw accurate conclusions about our population. Our standard deviation is going to help us visualize what the data set looks like, the measurements in terms in regards to the mean. So let's read this next part. 68% of measurements in the population will fall within the range defined by one standard deviation above and below the mean. What does that mean? 68% of all measurements. Remember that word measurement. Of all of those individuals taken in that sample size, 68% of them are going to fall within one standard deviation away from the mean. We are pretending that the computer calculated our standard deviation. And for the red data set, the standard deviation is 1, and for the green data set, the standard deviation is 4. Let's look at this figure down here. This is what we just talked about. From the mean, which in both of our data sets is 3, one standard deviation away from that mean, 68% of all data points are going to fall within that range. 2 standard deviations away from the mean, 95% of all of the data set. So basically all of your measurements should fall within plus or minus 2 standard deviations away from the mean. And you come back up here and highlight this. Here is where it says that 95% of the measurements will fall within the range defined by 2 standard deviations above and below the mean. And this graph is not really showing it, but I kind of drew little examples right here. If we were to show that curve between these two different data sets, the red data set is going to be steeper because the standard deviation, both sides from the mean, is only 1. So then 2 standard deviations would be 2 on each side, as opposed to that green population, 1 standard deviation equals 4. And 2 standard deviations from the mean, it would be 8 from the mean on each side. And so this curve for the green data set is going to be more flattened out to show that there is more spread in the data away from that mean, compared to the red one will be steeper because the data set is more clumped towards the mean. Does sample size matter? Yes, it is something you have to take into consideration when doing experiments. Let's take a look at this picture. Why does it matter? Well, if we take a sample from this population and our sample size is 4, look at what happens here. We randomly selected, and in this case, we would have 25% green and 75% purple. And so maybe we would, if we applied that to the population mean, we would have this 75% purple. It makes it higher. But if we take a larger sample size, so if we get some more info, look what happens. So now my sample size is 10. And we have 50% green to 50% purple. Just to let you know, the population mean is 50%. So as we add more individuals to our sample size, our mean mean becomes more representative of the population mean. And our goal is that our sample is a representation and can be applied to the entire population. You can see this demonstrated in these graphs to the right. This is a sample size of 4 on the top graph. Our population mean is 50. Our sample mean with a sample size of 4 comes out to around 60. Down here with a sample size of 16, you can see that our sample mean now is 51, and that is way closer to the population mean of 50. It is a better representation. You can also see that when the sample size increases, you start seeing a better representation of that normal distribution as compared to the small sample size as well. That's it for this video. Just to recap, we learned that populations are measured using samples and that the standard deviation describes the spread of measurements in our samples. Stay tuned for part 2 of this series where we learn about standard error of the mean and talk about how can we be confident our sample mean represents the whole population. See you next time.